For today's software engineering interview, we'd like you to explain strong versus eventual consistency. Large-scale databases used in highly available distributed systems often follow this model. We'll have one primary database node and multiple replicas which store the same data but help us increase availability. Strongly consistent databases like Postgres work like this. When a user sends an update, we first update the primary node, and then before we return anything to the user, we update all replicas. Once that's complete, we can return a success to the user. Any read request to any of these replicas after that point will return the updated data as specified by the user who made the update. Okay, and how about eventual consistency? Eventually consistent databases like DynamoDB work like this. When a user sends an update request, all we have to do is write to one database and then we can immediately return a success to the user. Eventual consistency guarantees that all replicas will eventually converge on the same value. So once that write is successfully returned, we can asynchronously update all of these to have the correct data. In that time though, a user might make a read request and get stale data. Okay, why would anybody ever choose eventual consistency? The two biggest advantages we get here are increased availability and reduced latency. If we have to wait for all replicas to return a successful update code before we respond, we have to wait for the slowest replica update. In this simple example, it takes only 20 milliseconds to write to the primary node, but 70 milliseconds to write to the other nodes. Additionally, if a node fails to respond, we would have to return a failed write, and this update would not be able to go through. If we're using a model where we support eventual consistency, we can accept that this just failed, and once it's restarted or we do something to fix the state of this node, we can synchronize it with the other databases offline, so we have increased availability.